I'll teach you to be happy. I'll teach your grandmother to suck eggs. Now, boys and girls, let's try it again.
Happy, happy, joy, joy, 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 joy.
All right, so our images for assignment 2 are experimenting with depth of field and motion. But since our first assignment we were editing in black and white, the challenge of this assignment, aside from the challenges I just mentioned, is to edit for interesting effects in color. And so we need to then understand how color works in the digital space. The color that is used in the digital space is what's referred to as RGB color. We'll talk about what that means in a moment. But it's a very different color space than what you may be familiar with if you've taken any art classes or anything like that. And how it works, right? It may seem complex as we get into this, but having an understanding of it will help you to then control the colors within your composition when you do editing later. My child is playing with her tablet, and the sound is coming through the monitor here in the living room. I don't know if you guys can hear that. If so, I apologize. I'm going to try my best not to be very distracted by it. But yeah, by the way, the snow also closed my child's daycare again. All right, so the color, the color system you're probably most familiar with is what is referred to as the RYB color space. RYB, or red, yellow, and blue, this is a historical set of colors that are used in mixing color, usually in paint or something like that, where the primary colors are red, yellow, and blue. And this is what is referred to as a subtractive color model. Subtractive meaning that when you mix the two colors, the resulting color is darker than at least one of the two colors. All right, so what do I mean? As it says down here, red, yellow, and blue make up the primary color triad, right? Red, yellow, and blue. And in this color system, those colors can't be broken down into any other colors. You can't take yellow and break it down into two other colors that you mix to make yellow. You can't take red and mix two colors to make it. You can't take blue and mix two colors to make it. Now, this is a theoretical model. There are so many things we could dive into that would take forever. But just understand that's the premise that this works on. All right? And that when you mix those two colors, you get the secondary colors, violet, orange, and green. All right? So mix yellow and red, you get orange. Now, orange is not darker than red, but it is darker than yellow, meaning that mixing red into the yellow has subtracted from the yellow. Right? The resulting color is darker than at least one of them. If you mix red and blue, you get violet. And although this color wheel, the colors in this image aren't perfect, violet is darker than both red and blue. And then in mixing blue and yellow, you get green, and green is darker than yellow. Subtractive. All right? And when we say a triad, we're talking about three equidistant colors around the color wheel. That is what this is referred to that we see right here, the color wheel. Complementary colors, then, and understand, I'm just kind of briefly going through why RYB color here. Even though it's not what we're going to use in photography, because this doesn't work in photography. I just want to give a reminder to anybody who's learned in this way, as well as sort of giving the basis for how color works when we mix it using paint and things of that nature. So complementary colors. Those are colors that are directly across from one another on the color wheel, right? Like green and red, blue and orange, yellow and violet. This, this is an assignment that was done by a student in the 2D design class. So some of those colors aren't perfect, but you get the point. When you mix two complementary colors, they neutralize one another, which results in various browns. And if you mix them in the right proportions, it results in a complete dark gray. It's almost black. That's also part of the subtractive nature of RYB. Then with RYB, you have to introduce black and white as additional colors to modulate the intensity or saturation of colors. And so, if again, as mentioned here, if you've had any sort of training in art at all, this is most likely the color system that you learned. It's not perfect, but it works. There are little things about it that are problematic, but on a theoretical level, it works, and you can mix the colors that you need using it. But it's not the only color wheel there is, because then there's the color wheel that we're going to use in photography, the RGB color wheel. RGB color model is an additive color model in which red, green, and blue light are added together in various ways to reproduce a broad array of colors. Again, RGB stands for red, green, and blue. Now that seems strange, right? Because if you're accustomed to the RYB model, green can't be a primary color because green can be made by mixing yellow and blue. But when it comes to light, which is what the RGB system uses, light, if you mix red and green light, you get yellow, right? Green light is a color that you can't break down into two other colors. So the main purpose of RGB color model is for the representation and display of images in electronic and digital systems, such as televisions, computer, digital photography, and video. Again, in all of these, the case is that light is what's being used. There's a whole thing we could get into. It would take too long right now in this particular lecture, but your computer screen is, of course, using RGB. But then once the time comes that you want to print the photograph, a completely different color system needs to be used, because when we're printing things, we're mixing inks. And ink won't mix like in the RGB color space. One moment. Augustina, can I help you? What is going on?
Honey, I was just getting the yellow cream.
Okay, well, can you either go to your room or settle down? Because I'm trying to record and you are bouncing all over the place with the energy of a spider monkey. Can you either go in your room or settle, please?
What's the spider monkey?
It's something that has a lot of energy like you have right now. I need you to pick one. What are we going to do? Okay, thank you. Okay. So, yeah, let's move on. Sorry about that. All right. Red, green, and blue, like I said, make up the primary triad of the color wheel, and the secondary colors are yellow, a color that it's referred to as cyan, and magenta. They make up the secondary triad. Those secondaries are just like in our YB color, are the result of mixing two of the primary colors in equal proportions. So red and green will give you yellow. Again, if you're used to mixing paint at all, that makes no sense. But that's how it works with light. Green and blue create cyan, and blue and red will give you magenta. Now, as I mentioned, the RGB color wheel is additive meaning that if you mix two colors, two of the primary colors, the resulting color in the middle is actually brighter than the two colors that were being mixed. And that might not immediately make sense until you remember that what you're using is light. And so if I take a red light and I add a green light to it, the two lights coming together are now stronger, so they're going to be brighter. Or a green light and a blue light coming together. The light overlaps, and the light that we get is now stronger and therefore brighter. So to form a color with RGB, you need 3 light beams. And so on your screen that you're looking at me right now on, every single pixel that you see on that screen is being created through 3 light beams. 1 red, 1 green, and 1 blue. They have to be superimposed, for example, by emission from a black screen, right? So whatever you're watching this on, whether it be your computer, whether it be your phone, whether it be the TV, and you're casting this onto the TV, right? Before you turned it on, that screen was completely black, right? That's forming the black color, right? It's the absence of any light. And then all these colors that you see are being projected from that. Or by reflection, where the light hits a white screen and bounces back to our eyes, as is done in the classroom when the light hits the screen at the front of the classroom. Each of these 3 beams is called a component, and that's a term that you should become familiar with, right? A component of that color. So we will talk about the red component of a photograph, or the green component of a photograph, or the blue component of a photograph. And each of them can have an arbitrary intensity from fully off, meaning that light beam is not giving out any color whatsoever, to fully on, where it would be a pure red, or pure green, or a pure blue, with intensity in between where that light isn't as intense, right? And we measure this intensity in digital color from 0, which is off, to 256. Nope, that should be 255. I'm sorry. 255. So there are 256 settings, which is where I got confused there and accidentally put a 6. All right, 0 is fully off, and 255 is full intensity. And it may not make a whole lot of sense to you right now, but you'll see how that works here in a moment. The result of mixing all 3 primaries at full intensity is a pure neutral white. That's what you can see here in the center of these 3 circles of color, right? If you have them all mixed at 0 intensity, you have black, because none of those lights are on. So this white here is being created by having all 3, red, green, and blue, all 3 lights are shining at full 255 intensity. So our eyes see white. But if we could zoom in really closely to those pixels, which we will in a moment, we would see that each pixel is made up of these 3 colors. Where you have black, they're all shut off. So in these areas here, until my mouse slides into view, there's nothing, right? None of the lights are turned on in these areas. When primaries are mixed all at the same intensity, but less than full intensity, the result is gray. The lower the intensity, the darker the gray, right? We'll look at an example of that, so don't worry. If that didn't make sense, don't worry, I'm going to show it to you. Each primary has a secondary color, right? So red, cyan, green, magenta, and blue, yellow, right? They're across from each other on the color wheel, just like in RGB color. That, when mixed at full intensity, also results in white. So if I mix red and cyan, I'm going to get white. If I mix green and magenta, I'm going to get white. And if I mix blue and yellow, I'm going to get white. Again, that's one that if you've had any training with mixing paint, it just doesn't make sense. Because yellow and blue are what you mix to get green with paint. But in digital color, it will give you white. And if you mix any two complementary colors at the same intensity but less than full intensity, the result is a gray. And the lower the intensity, the darker the gray. And when I talk about the intensity, I'm talking about those numbers, right? From 0 to 255. And again, please ignore that 256 that I accidentally typed in there. All right, this provides then, just using 3 component colors, a total range of 16,777,216 colors, most of which our eyes can't even distinguish the differences between, right? but because it's just the slightest change of intensity that gets us all these different colors. But because we have essentially 256 levels of intensity for each of these 3 color components, we can get those millions of colors on the screen. All right, so here's what I was just talking about, right? If I take this little area up here, right, where the red, yellow, white, and magenta are all coming into contact with one another, and zoom in very, very tightly on the screen here, I can see that the pixels are being made up of colored light. Now, here it's a little harder to see because the light is still trying to blend, so I'm going to move in a little closer. And so you'll see here that what appeared to be white, when we zoom in tightly, is actually a pixel. Each pixel is made up of 3 colors of light, blue, red, and green, that are shining outward, and as they do so, the light sort of blends and looks white to us. Where we thought we were seeing yellow, right over here, yellow, we're actually seeing a pixel that has the blue turned off. Notice how where the blue is, let's say over here, right, where you can see the blue, that's turned off. There's black in that area, right? And we have red and green turned on. And the 2 colors projecting outward from that pixel mix in our eyes and look yellow. The red up here only has the red component on and nothing else, hence these black areas where the blue, and then on this side where the green would normally be, right? Only the red is on, and each of our pixels here in what had been, what appears rather to be magenta right here, we look up close and we can see we actually have a blue and a red component next to one another that are turned on, and the green component is turned off, and the blue and the red light are mixing to give us the impression of a magenta color. Right? Each pixel on your screen has those 3 beams of light, a red light, a green light, and a blue light. And it's the intensity at which each of those is turned on and the way our brains sort of mix the colors that do the trick. Right, let me go back to it. Because still, when you look at that, right, there, and all we see is yellow. All we see is yellow right there. Right? But get up close and you can make out that it is a red and a green light, but still our eyes still kind of want to turn that into yellow, right? Now, here's how this works. So this is in GIMP, when we create a color, we can do so by manipulating the red, green, and blue. This stuff up here we're not going to worry about right now, right? The hue, saturation, and value. We're just going to talk about RGB. All right? So in this particular case, right, to make this color right here, this orange color, we've turned the red all the way on, 255. Right? That is full intensity. The blue we have set at 0. So the blue component is not turned on at all in this color right here. And then we took the green and turned the green up to 90, right? Which is not even quite halfway to full intensity. So what that does, you remember that mixing red and green makes yellow. But if we take the green down in intensity, we're not going to have a yellow anymore. We're going to have something that's more red than it is yellow. Hence, orange. Now, this particular green here, right? It's a darker green, right? This green here. And you see here's where it's sort of located in this whole big field of green. It's a darker green. It's not super dark, right? But it's up in here in this range. So how did we create it? Well, we've got green, which is not very high in intensity, 133, but still it's the highest of the three, right? The red and the blue are nowhere near as dark as as intense as this is, right? But remember that green and red will create yellow. So a little bit of red put in here keeps this green from looking too that's hard to explain. Well, look up here in this corner, right? That's the kind of green that we would get by mixing green and a little bit of red. It would be this kind of yellowy green that's up in here. But by not mixing them at the same intensity, it darkens this a bit. Then the blue, just a tiny bit of blue is added, and then that makes for this red and this blue to kind of come together to create something of a reddish magenta, and that being mixed with this green darkens it a bit. Again, because both of these are turned way down, so they're already kind of darker, and the green itself is a bit darker because it's turned down in intensity as well. And that gives us this green, but a green that's kind of a gray green. Then, as I mentioned, if we take the three colors, red, green, and blue, and we mix all three at the same intensity, but less than full intensity, we will get a gray. So all of these have been mixed at 104 intensity. And that gives us this gray right here. And it's a complete neutral gray. It doesn't have any warmth or coolness or anything. It's a neutral gray because all three are at the same intensity. All right, so then we take, say, a photograph like this, right? This beach scene looking out toward the water. And this image is made up of three components. There is the red component, the green component, and the blue component. Notice that where the image is the brightest, this area right in here, which is almost white, in all three images, that's the area where the color seems the most intense, right? Because in those areas, the light is much more intense. Notice, let's say in areas where we see a lot more blue, let's say in the sand here, right, where things are a lot more blue, that in the red and the green, those areas are darkened a bit because they've been taken down in intensity, but the blue still seems pretty saturated in this area, right? That's why this area right here feels like a grayish blue. We look at, say, where the green grass is in those areas, and you'll note that in the green, like that grass right there, is much more intense than it is in any of these spots, although it's not as intense as what's immediately beyond it in the sand, because the sand out there is this color that's a bit lighter. And so we can take an image that looks like this, and one that looks like this, and one that looks like this, and combine all three to give ourselves a full color image with the full spectrum of colors. Now, understanding all those things, of course, will help you in editing your photos in color, because you can know which direction you might need to shift your colors to get the reaction, or rather the effects that you want within a photograph. But there's one more thing that's kind of important. It happens within your camera, though we can control this a little bit in editing. And this is very dependent upon the things that we were just talking about. And it's something that's called white balance. White balance is important. Maybe you've never had to give it solid consideration while taking photographs, or maybe you're already familiar with it. Most cameras will already have an automatic white balance setting. Sometimes, however, that automatic setting can cause problems for you when you don't mean for it to. So white balance, what even is it? White balance is a camera setting that adjusts how colors are rendered in an image. Specifically, the correct white balance should result in the color of light appearing as close to neutral, white or gray, as possible. And this is done in camera by determining the temperature, the warmth or coolness of the light that's entering the camera and adjusting by adding the complementary color of that temperature into all the pixels within the image. So, hang on. Yes. Okay, well, you didn't have to tell me about that. You could have just gotten it. All right, I love you. Hey, bye-bye. So, what your camera does is it looks at the color of the light that is coming into the lens, and it adjusts. Our own eyes do this all the time. Right? That's what it's mimicking. We step out into a really bright sunny day, and surely you have noticed, like when you're stepping from inside to outside, there will be that moment where for a while everything looks really weird and blue, right? Like the whole world just looks super blue. And then your eyes start to adjust, and then boom, everything looks normal again. Well, the reason that happens is that the light outside, the light when we go outdoors, is very cool in temperature. It is very blue in nature. That light then needs to be adjusted in our eyes, or else the whole world doesn't look quite right to us. And so our own brains will take that light outside and will add a little bit of yellow to it. Right? Remembering that blue and yellow are across from each other in the RGB color scheme on that color wheel. And by adding a little bit of yellow into it, the blue gets neutralized, and all of the whites and or neutral colors that we see look normal to our eyes. Right? Then our eyes have adjusted to that, and then we step inside. Right? Sure, you've had this experience as well. And the colors all look really weird again. They might either look very green or very yellowy, or sometimes they'll look kind of magenta-ish. It all depends on what the temperature of the lights inside whatever building you've walked in are. And that's a matter of, right, our eyes were adjusted to that very blue light outside, so our brains are adding all this yellow to all the colors. And then we step in, and the lights inside have a different cast to them. Maybe the lights inside already are kind of yellowy in color. Maybe they're kind of green in color, what have you. And our eyes adding that yellow to the color is mixing it, making it look really weird. And then slowly our eyes adjust and it looks normal again. Cameras do the same thing. As we can see with this image up above, right, where there's different colors and at certain different intensities that are being added to each version of this photograph. I did one with my own photograph here, right? So if a camera looking at the light coming in decides, ooh, that image looks very greenish in color, so let's add some magenta to the image in order to balance out the white. Right? And so what that can do is give us an image like the one we see here on the left, where you'll note, compared to the other two images, it looks much more magenta-y, right? In the middle here, the camera, if it's detecting that there's a lot of blue light coming into the image, adjust by adding yellow to all of the pixels. And you'll notice that as a result, this image in the middle looks a little more yellowy. This one certainly looks warm as far as sort of warm reds and purples. This one feels much warmer because it's leaning toward yellows and oranges. Then we come over here where the camera may have picked up that the light coming into the camera looked a little too yellow. Or in this particular case over here, because it's probably not, right? This is an outdoor photograph. It's very sunny, right? The light coming into this camera would be blue. If the camera did not adjust its white balance, this is the image we might get. One where instead of looking white, like her shirt should, her shirt looks very blue in color, right? Because this is what happens with white balance. It's the neutral colors that end up looking a little off and wrong. And by extension, other colors get dulled down, right? You can see it happening in the hat here, where the hat looks very nice and orangey there, and then it comes over here, and that orange gets dulled down to almost like a grayish, I don't know, what would you call it? A grayish mauve, right? So you may have had this happen. It will often happen when you're trying to take a photograph of a sunset or a sunrise. The colors are just gorgeous. So you pull your camera out. It's very often with our phones, because our phones really like to use an automatic white balance setting. And you snap a picture of that gorgeous sunset, and then you look at your camera and you're like, where did all that color go? And the reason is that because those intense colors are coming into your camera's like, ooh, okay, it looks like the white balance is off. There's a lot of orange coming into the camera. So if there's a lot of orange coming into the camera, that orange is kind of like red. So I should add cyan to this. And so your camera adds cyan to all the pixels. And now all of your colors have been dulled down. So most cameras will also have a place where you can go in and manually set the white balance. This is something that once I see you in person again, we'll take a look at your cameras and figure out how to do. Some cameras will also even let you manually set your white balance by going into the manual settings, going to white balance, and then pointing your camera at something that is white. And then telling your camera, okay, that is white. And then no matter what else happens while you're taking your photographs, it will always stick to a white balance that's trying to make the colors look the way it thinks it needs to get that white thing that you pointed at earlier. Now, why is that important? Well, excuse me while I readjust. So I've had plenty of times when I was taking photographs of scenery. I was outdoors taking pictures of scenery, and for a series of photographs. And it had just hadn't occurred to me, and I had left my white balance on automatic. So I take several photographs of the scenery, and then I have somebody step into the scenery, right? They're fairly close to the camera, let's say, and they're wearing, let's say, a yellow shirt. Now, suddenly there's this big portion of the image that's yellow. And the camera says, ooh, it looks like the light has changed out there because I'm getting a little more extra yellow color in here. And so what does it do? It decides to add more blue. And so suddenly in what is meant to be a series of photographs that would be scenery, and then person comes into scenery, right? Suddenly I have this one photograph that looks so different from the others, because now, rather than say really nice, crisp green field, this person steps into it wearing a yellow shirt, and now suddenly their yellow shirt is dull. It's a dull yellow, and instead of that crisp green field, I've got a field that's kind of bluish green, right? Because the white balance added blue to all of the pixels. So we'll talk about also playing around with our white balance within the camera when I see you again, but also when we talk about editing our photos in color, getting correcting any white balance mistakes within a photograph is one of the things that we will talk about in class as well. Okay, so there we are. I know it's a ton of information. As I said, all you're really responsible for is watching this and providing me the information that I ask for in the assignment in Google Classroom. That's it. If we meet on Wednesday, wonderful. If we don't, I'll let you know what we're going to do on Wednesday. Take care, everybody. Please stay safe and stay warm out there. Hopefully, we'll see you guys soon. All right. Bye, everyone.